So in this section, we are going to be looking at systems of inequalities. So earlier in this chapter, we learned how to graph a system of linear inequalities, or linear equations rather. And now we're going to be working with inequalities. So we're going to have our inequality symbols here, but they might not just be linear equations. They could also be quadratic or circles or any other type of function. So first thing, if we have an inequality without that equal to sign, we need to make sure we're drawing a dashed line. And if we have the line underneath, we need to make sure we're drawing a solid line. And if we're talking about a linear inequality, so this is just for linear, inequalities, if the inequality is pointing towards the y, you're going to shade above the line. If it's pointing away from the y, you'll shade below the line. And this is only true if y is positive. If y is negative, then you do the opposite. Now, if you're working with nonlinear inequalities, you're going to need to use test points instead of just using this shading up and down thing. So let's do our first example here. We've got x minus y is less than 1. And so you can either use the finger trick that I've showed you before for graphing this, or you can get it into y-intercept or slope-intercept form. I think a lot of people prefer slope-intercept, so I'm going to go ahead and do that here. And first I'll go ahead and subtract x. And then I'm going to divide by -1. But remember, when you divide an inequality by a negative, you have to flip the directions of the inequality. And this will become a -1 and a positive x. So let's go ahead and graph that line. My y-intercept is -1. My slope is +1. Up 1 over 1, up 1 over 1. And you want to do as many points as you can to get the most accurate graph you can. So I'm going to do a lot. And we want a dashed line, and this actually already kind of looks like a dashed line, so let's just go over it a little bit more. And then we're going to be shading above the line since it's pointing towards my y and my y is positive. I'm just going to do that lightly in pen real quick. And then I'm going to actually get the other one in slope-intercept form as well. So first thing I'll do is subtract 2x. So 3y greater than or equal to -2x plus 12. And dividing both sides by 3. And my y-intercept is 4. 1, 2, 3, 4. My slope is -2/3, so I can go down 2 and over 3, down 2 and over 3, and I can do this a few times. This inequality will be a solid line. And we are shading above here as well. So when we're doing these, I really like using different color highlighters because I think it's easiest to tell where the overlapping area is, and that's where our solution is. So this one was above this line, and this one was above this line. So what we're interested in is this overlapping area here. This is what my solution is. Okay. All right, let's do another one. And now we're not just working with a linear inequality. Here we have the equation of a circle. So let's graph our linear one first. -1, my slope is 2/5, so up 2 over 5. I can go the other way as well, down 2 and over 5. And this is a dashed line. And I can still follow the rule for shading here about above or below. This one will be shaded above, because this is linear. And then I have a circle. So this circle, the center is at 0, 0, and then my radius is 3. So center at 0, 0, and I'm going out 3 in each direction, and this is a solid line, so I can graph a solid circle line. And the way we tell where we're shading, it's either inside the circle or outside the circle. And I'm going to use a test point, and the easiest point to plug into this is 0, 0. So if I plug in 0 for x and 0 for y, I'm checking to see, is this true? Well, 0 plus 0 is 0, and 0 is in fact less than 9. So this is true. So wherever my test point is, if it's true, we shade in that area. If I got a false statement, let's say I got 16 on this side, then I would be shading not where the test point is. I would be shading in the opposite area of the outside. So what we're interested in is this overlapping part of my circle here where it's both orange and green, and that would be my answer. It's not super dark. Let me kind of distinguish it a little bit better here. It's this kind of half circle looking thing there. All right, let's do some more examples here. And now we have more than just 2 equations. We have 3 equations, and that's perfectly fine. We can do problems with 3 equations. Let's look at the first one here, and this is a quadratic equation. And my vertex is at 0, 4, and it's going down. So let's go ahead and graph that quadratic function here. And you know how to graph quadratic functions, so that should be no problem. And this is a solid line, so I'll go ahead and graph that solid line. Now let's go ahead and choose a test point. Here our test point would either be something outside or inside the parabola. I'm going to choose 0, 0, and if we plug that in and we get a true statement, that means I'm shading in here. So plugging in 0, 0, 0 less than or equal to 0 plus 4. That would be 0 less than or equal to 4, and that is true, so that means I am shading inside here. So I'll do that. Actually, I'll do it in green and just in pen first, and then I'll go over the overlapping area later. So we very lightly shaded in here. Next one is a linear inequality, and I'm going to go ahead and get y by itself, x minus y greater than or equal to -2. I can subtract x. And I can divide by a negative, but remember I have to flip that inequality. And my y-intercept is 2. My slope is +1, up 1 over 1, up 1 over 1. I'll do as many points as I can fit here. That way we get the most accurate graph possible. Oh, yeah, good. It was solid. I should have checked first. Yep, it's solid. And then the other one's going to be dashed, so I need to be careful with that next one. And let's, we need to talk about shading. We're shading below the line because it's away from that and y is positive. So we're below that orange line there. And then this last one, y is greater than -5. This is a horizontal line at -5, and it's dashed. And we're shading above the line because it's pointing to the y. So my overlapping area is below this orange line, above the purple line, and inside the parabola. So that would be this area here. All right, let's do a couple more. Here we have another linear equation, so I'm going to go ahead and get y by itself. Actually, we've got a couple linear equations. Subtracting 2x, I have y is less than or equal to -2x minus 2. Y-intercept of -2, slope of -2. Let's plot as many points as we can get here. And this is solid. And we are shading below. And the next one, I can also get y by itself. I'll subtract 6x, so I have 3y greater than -6x plus 6, dividing by 3. My y-intercept is +2, and my slope is -2. So notice our slopes are the same. So right now I already know that these are parallel lines, and this is dashed, so I'll go ahead and draw a dashed line. And this one we're shading above. Well, looking at this, we can see there's no overlapping area, so there's nothing for me to highlight. That means there's no solution because there's no overlapping area of these inequalities. All right, let's look at our last example, and both of these are linear vertical and horizontal lines. So here we have a horizontal line at -1, and it's dashed, and it's less than, so we're going to shade down. And here we can go ahead and divide by 2, and we get x greater than or equal to -3. And so vertical line at -3, and it's solid. And there's no above or below here, but we want to think, where is x greater than -3? Is that to the right of this line, or is that to the left? Well, bigger than -3 would be to the right of this line. So my overlapping area is going to be this space here, where they're both shaded. And this brings us to the end of section 5 and the end of chapter 5.